We're going to do Unit 1, Chapter 1.6 in Unit 1, so it's infinite sequences. Like I said, we are familiar with these patterns from, hopefully, Math 20. I'm not sure how much of those you guys did in Math 30, but you guys do any in Math 30 at all, of the arithmetic sequence and stuff? So anyways, at least I know you've seen this stuff before. So just a quick review of that. Remember, a sequence is a pattern, okay, an infinite sequence, which just means it's dot, dot, dot. It goes forever. So you have your first term, second term, third term, fourth term, etc. We label those as T1, T4, whatever, T sub n. Okay. So example 1, list the first 5 terms of the sequence defined by T sub n equals n over n plus 1. So how would we find the first 5 terms? What would we do? Not complicated. Yeah, we just plug 1 in for n. Yeah, just plug 1 in for n, plug 2 in for n, etc. Okay, so Rye, what's term 1? 1/2. What's term 2? Jeremy? 2/3. Kate, what's term 3? 3/4. Rachel? 4/5. And Christian? 5/6, right? You got the pattern? 5/6. Everybody's 100%. Good job. Okay, good. All right, so, and then we're going to look at that graph in terms of like what it looks like. Okay, so if we look at that, just kind of generally here, we got 1 here. We'll say this is term 1, 2, 3, 4, 5, 6. So term 1 was 1/2. Term 2 was 3/4. And this kind of keeps inching up closer and closer to what? Yeah, it keeps getting closer and closer. Will it ever get to 1? No, it'll never get to 1, but it is approaching 1. Does that make sense? So it'll never get to 1, but it is approaching 1. Oh, wait, some of you guys are writing this down here. And that makes sense because no matter what you do, n is going to be less than n plus 1. No matter what you do, n is going to be less than n plus 1 because n plus 1 is whatever n is and then add 1, so you always lose, right? Okay, so it's always going to be less. So with that being said, we know it's approaching 1, and whenever I say the word approaching, I hope we're thinking what that's about limits. Okay, say it's approaching 1. So that means that we can say that limit of n approaching infinity, so as our numbers get bigger, okay, of n over n plus 1 equals 1. Because you see what it's approaching. So in general, okay, you can do limit of an n approaches infinity of a term, like a term function, like this, will equal its limit. So we can take limits of infinite sequences to see where those sequences are going. Now, by doing that, let's make sure we understand what that's saying. It's saying that the sequence is approaching, not the sum. We'll get to series tomorrow. Series, remember, different sequence was the pattern. Series was adding the pattern, remember? So we're just doing sequences today. So all this means is that we're just saying, if we take the limit of this pattern as it keeps going, 1/2, 3/4, 5, 6, all the stuff we kept doing, if we keep doing that all the way, that's going to approach 1. We can safely say we're going to get 100 over 101, 200 over 201. We're going to get really, really close to 1. So we call it, our limit is 1. Okay. All right, so with example 2, so find the limit of this one. Go ahead and try this one, see what you think. And kind of use logic here if you can. You can even try some. Write some terms out. Okay, so find the limit as n approaches infinity of 1 over n. So what are the, if I just go through 1, 2, 3, 4, what does my sequence look like? So what's the first? What's my first term? 1, then 1/2, 1/3, okay, and 1/5, and we get tired of doing that. Okay, 1 over 1, 1 over 2. Okay, good. And so it's getting smaller every time. So then, if it's getting smaller every time, what would you guys think it's approaching? Good, it's approaching 0. That's correct. So therefore, this answer would be 0. It approaches 0 because the number keeps getting smaller. Okay, this is because the top, now this is almost a logical, like a number sense thing, 1 isn't changing, but n is. So the 1 is kind of like standstill, and the n keeps getting bigger, so it keeps making us get smaller. Whenever your bottom is growing faster than your top, it's going to go to 0. Okay, whenever your bottom is growing faster than your top, it's going to go to 0, which makes sense because if your bottom is getting bigger and your top isn't, it's going to stay, it's going to keep approaching 0. Okay, so that's why this would look like, so again, I'll rewrite this, I have it in my notes, but as n approaches infinity, 1 over n, the limit of that is 0. Okay, this is actually, okay, going to be a, I have on the next page. I'll do it on the next page when I draw this graph, so I'll just pause for a second, try to get my notes to flow better today. Okay, everybody have this? We're good? So this creates this definition here. This definition is simply that limit as n goes to infinity with an n to the r, where r is bigger than 0, like pretty much a constant over a variable, is always going to approach 0 because the constant's growing. Or excuse me, not the constant, the variable is growing. Okay, and what this picture, the 1 over n looks like, if you forgot, that's a hyperbola, and it looks like this. So that makes sense. This line right here, as it keeps going forever, it's getting closer and closer to 0. Technically, it won't ever get there, but it's approaching there. So that's what we call it with our limit. Okay. All right, let's try. I want you guys to try example 3. You're probably going to get stuck, but if you don't, that's great. Try example 3 here. See what you can do for this one. All right, so you probably got stuck. I'm going to show you the long way here. I'm going to tell you where it came from, and you'll be kind of a light bulb moment. Okay. So what I'm going to do is right now the problem is the other ones were just n's. So we kind of simply see, oh, the bottom's growing faster than the top. But this one has an n squared on top and n squared on bottom. So it's kind of like, okay, well, which one's growing faster, right? So what I'm going to do is I'm going to take out the n squared of it. And so what I mean by that is I'm going to go ahead, I'm going to divide the top by n squared, and I'm going to divide the bottom by n squared. Just to kind of lower things to see if that helps me see anything better. Okay? And so what that does is, well, what's n squared over n squared? 1, right? And then what's an n over an n squared? What's that reduced to? Other way, 1 over n, yeah? Right? 1 over n. So that's what my top is. My bottom, n squared over n squared cancels, so I get a 2. And then I have 1 over n squared. Okay, now if I'm doing the limit as n goes to infinity of these, what do we know about that guy? We just did it. What does that equal? 0, right? And by our limit properties, remember, we can break everything up into multiple limits. So I'm really taking the limit of this, 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 and this separately, if I wanted to. Okay? But my point is, it's like Ryan just said, this limit is actually 0. So 1 minus 0. Okay? What about this one then? Yeah, it's still 0. That's the definition we just did. Variable on the bottom, constant on top. The bottom's growing, the top's not. That's also 0. So then what's my limit? Yeah, it's 1/2. So your answer is 1/2. Can anybody maybe look up there and see where that came from maybe? A little bit more shorthand instead of doing the longhand. What's that? Nope, but close. You did, that'd be minus, you did this, you solved for 0 here. So you're... Starts with a C, doesn't it? Okay, coefficients. Okay, so where it comes from is this. What is my highest degree in both of these? 2. What's the coefficient in front of the highest degree here? 1 here, 1 over 2. That's where it comes from. Okay, it's that easy to see. Okay, instead of doing all that fraction work. Okay, but anyways, my point is, these are my biggest exponents. What's the ratio of their coefficients? 1/2. Now, would that work? Let's just stay on topic here. Would that work for this? It would not, because they're different degrees. So on this one, let's just see what you guys think. What would that limit be? 0, because the bottom has a cube. It's growing a lot faster than the top, so it's going to get bigger faster. Okay? Does that make sense? Perfect. Are we good? On to the next here. All right, example 4. Find the following limits if they exist. I'll let you try these ones now. See if we can get these going. So, all right, anybody have anything for me on this one? What's the limit of this one? Right, you can only get, it just keeps doing what? 1, -1, 1, -1. So what do we talk about if it just keeps bouncing back and forth between the same numbers? It's not, well, yeah, it's just continuous, but it doesn't exist. Okay, so it doesn't exist, that's just the answer. So A, so you guys are right, it just keeps going 1, or -1, 1, -1, 1, etc. So it's not approaching anything. So it has no limit. So your limit does not exist. If it's not approaching anything, there is no limit. Okay, with that being said, how about the second one? It's approaching 0. Very good. Another way you can look at this too is 1 to the n is nothing, right? Remember, when you have an exponent, it goes to top and bottom, but that's the same thing as just 1 over 2 to the n. And now this kind of fits more into what our picture of our definition was. If there's a variable on bottom, something's going on the bottom. Okay, so yes, good. This is 0. Okay, and if you just looked at that pattern to start, B would go 1/2, 1/4. What would that be next? 1/8. Is it 8th or 16th? Yeah, you're right. 1/8. Okay, etc. Okay, very good. And that kind of yields us to this one. Okay, that yields us to that definition there. So the absolute value of R is less than 1. So that's a fraction, right? That's saying -3/4 or +3/4. Then the limit of that R to the n is 0. So pretty much any fraction, okay, any fraction, this is positive, negative. Why is it for negative? Let's try to make sure we understand the definition here. If I did -1/2 to the n, think about it. What's -1/2 to the n? Well, 1 is -1/2. What's it squared? 1/4. Because it's -1/2 times -1/2, right? And if I do it again, it's going to be -1/8. So even though it's flipping the positive negative, it's approaching 0 from the positive negative. It keeps coming in at it. So both directions. So that's why the definition says negative fractions work too. Okay? So it keeps flipping back and forth. Does that make sense? Okay? So it keeps flipping back and forth and it's still approaching 0 because it's still getting smaller. Because like next one would be what? 1 over 16, right? -1 over 32. So keeps going and going. Okay? All right, very good. All right, and then we're going to take a little look here at number 5. Okay, so the Fibonacci sequence is defined recursively by the equations f of 1 is 1, f of 2 is 1, f of n is the previous two terms added. That's what that means. N minus 1 means the previous term, n minus 2 means 2 terms ago. Okay, so what they're saying is find the first 8 terms of the sequence. So I want you guys to see if you can find the first 8 terms. So they give you 1 and 2. So 1 is 1, 2 is 1, and they want you to find 3, 4, 5, 6, 7, and 8. So I'll give you a second here to go ahead and try to do that. All right, so going through these, the reason, so just so you understand what this means, that means n has to be greater than or equal to 3. That's because they give you 1 and 2. So you don't know what f of 0 is, so how could you add the previous 2 terms if you didn't know what f of, what before f of 1 was? So that's why it says you have to do 3 or bigger. That's what you are doing. So you have 3. Austin, what'd you get? Right, it's 2. 1 plus 1. Okay, good. And Emily? F 3. 2 plus 1, 3. Good. F of 5, Rye? 5. The previous 2. Okay, good. 8. Rachel? 13. 8 plus 5. Yeah, the last two. And then 21. So there is your Fibonacci sequence. Okay? All right, and that's it for 1.6, so not quite as bad today.